Hello and welcome to this Mastering the Machine Automation Academy video for the 11th of March 2023. Today's topic was advanced PLC programming using RSLogix 5000, FactoryTalk Studio ME, and simulations. And this is based on a class that I taught this week to some interns at Automation NTH. Hope you enjoy it. This is a Automation Academy Mastering the Machine webinar for the 11th of March 2023. And today's topic is going to be advanced PLC concepts using RSLogix 5000 and FactoryTalk View ME, which I use with an emulator. Little bit of the basics out of the way before we get started. What is the Automation Academy? This is a membership site that I created about 2.5 years ago, and I just put a lot of information on it. It has a lot of videos and things like that. It has a library of training and technical documents, or probably a couple of hundred documents and some software on there, things like that. There is a community called IO Central that people can join for free. It is meant to be kind of a social media site like a LinkedIn or a Facebook or that sort of thing, but there's honestly not a whole lot of people that hang out there, which until it gets some momentum, that just doesn't happen. And we do these Mastering the Machine webinars every 2 to 3 weeks. You can find more information at all these different websites kind of listed on here. This is my company website, and you can see the academies under that. There is a blog, the Automation Primer, which I honestly don't keep up with very much anymore. It's about 11, 12 years old and that sort of thing. So the reason that I am doing this course today on this and making it not just a informational webinar is I teach this class 2 to 3 times a year for a company called Automation NTH. And Automation NTH does life sciences machinery, very complex machines, very large programs. And they have an internship and apprenticeship program where they take people in for 3 to 4 months. They're usually graduates or people about to graduate from local universities. And 2 of these people are currently at Middle Tennessee State University finishing up their one's doing mechatronics degree. The other one is doing a, I think, mechanical engineering degree. This fellow has already been hired. He's been working there for about a year, but he hadn't taken this class yet, so we put him through it. You can see here a little piece of the lab, and we have all these little trainers in here and things like that. But obviously, you can't play around with the really big machines. So what we do here in this class is we do a simulation, and I teach people how to simulate complicated things. So a little more complicated than just things like machine cycle start and auto sequences and things like that. A big concentration on this week's class was part tracking. So what part tracking is as components make their way through the machine, a lot of times you need to log information about those parts, like physical parameters. Did they pass or fail certain stations? Where is the part? That sort of thing. What's its serial number? When did you start making the part? When did you complete the part? And did something fail? And did you accidentally get a good part in the reject bin, or vice versa? Which vice versa doesn't work in the medical industry. If you have a good part or a bad part that makes its way to the good parts bin or the output, that's really bad, right? It can kill somebody. So it's very important when we go through these classes that we reinforce the fact that bad parts can't make their way into the good parts bin. So anyway, that's what this class is about. I've been teaching this since about 2017, and it's migrated. We used to use real PLCs, but the problem with real PLCs is they have real I/O and they just have push buttons and pilot lights and things like that. And it's really hard to simulate a real machine. So it's kind of migrated its way into building your own application right? And then running it with feedback from the inside of the program. I'm going to go ahead and show you a complicated program first. And this I show to a lot of times to the students, honestly, to scare them because they're working for a company that writes very complicated programs. Where is it? Let me see here. We'll bring faster. There we go. So it's hard to even go into the individual the routines and things in here. This program, we call in Allen Bradley, you have a task, right? You have a continuous task or a periodic task. You can see here, all of the tasks here are periodic tasks. So they run on a time schedule. And this one runs at 30 milliseconds. This one runs at 2 seconds, right? So you don't even see a continuous task in here. It would appear usually at the top, and then you have some other, here's a periodic task running some motion control. Here is a safety task, right? They use safety PLCs and everything, all the safety things are connected into safety components. And so these are all safety programs. So what we call in these tasks, the individual sections, we call them programs. They do not run independently. They run within the task, one after another. And so I'm just going to pick one, and we'll say this is a heart height measurement. This one's a dispense robot. So here's a robot program. It has its own inputs. It has an auto sequence. It has a homing sequence. It has outputs. It has events, and Automation NTH's programs. Events include warnings and faults, alarms, informational messages, things like that. But the faulting for the machine and alarming is within the events routine. And then there is a system routine, and the system routine kind of connects all the other routines. So you see here, just this one program has 6, 7 routines in it, 8 routines, including the main. One of them here is in structured text. They do their initialization in structured text. The rest of them are pretty much in ladder logic. Allen Bradley is very heavy on ladder logic. It doesn't use a lot of function block diagram or structured text. You can, right, up to you. But the template for Automation NTH uses quite a bit of ladder. So here in the US, that's a very popular language. So that's what we use. I'll pick another one here randomly. There's some cameras. Where's something? Here's UF handling. I forget what UF stands for. But you can see here, once again, there is a kind of a common outline for all these. Initialization of the routine. Inputs, they use something called an AOI to handle the inputs. I'll be explaining what that is. I go through that in the class. And the students already know what AOIs, the DI handler AOI at least is by the time they get to my class. And then I introduce them to another 10 or 15 AOIs, and I have them build their own AOI so that they understand how to do that. So you can see here, work material info, load material info. This is exchanges of information to a database. So somewhat complex, right? Dealing with ignition, which is a SCADA system, and each one of these systems have ignition on it. So pretty complex thing here. It's got 70 programs in it. If I go down to the hardware configuration, it has probably 200 individual IP addresses for different things within that system. So very complicated here. This is an L84, which is a big ControlLogix full rack PLC, but you can see all these other racks down here, right? The remote IO for the TED system, and all these abbreviations and things. You can see cameras here. You can see robots, lots of robots. I want to say there's 22 robots and 40 plus cameras, weigh scales, lots of different things in here. It's doing a lot of physical manipulation and a lot of inspection. That's what their program does. So very complex. You can see that these programs get really big. very quickly. So just finding things within it alone can be very complicated, cross-referencing, et cetera. So what I do in these classes is I try to slowly introduce these students to more complex programming after they've done their initial basic PLC learning, and they've done little projects using these little conveyors and real hardware. Like there's a little conveyor, it's hard to see back here, but they do some work with that, and a little reject mechanism. And then I introduce them to this class. So this class, I have them start a project from zero, and they will set up their main task. They'll set up some IO, but because I use an emulator, as soon as you download to the emulator, you lose your IO. You can't download real cards to the emulator. This is what the emulator looks like. And you can see here, I've got an emulate processor in slot 2. If I go into the hardware configuration of things, you'll see that maybe the processor itself is also in slot 2. And then all I do is replace the real processor with an emulator processor. But when you download it to this system, even if it's in the same slot, you lose all of the IO. The IO doesn't get added to this. So what I do in the class is I use simulated IO. And the simulated IO is very simple, right? I go up here and I create a simulated digital IO, and I just create a bunch of DINTs, right? So what you see here, right, is obviously the equivalent number, but simulated IO slot 1 has 32 points in it. Some are on, some are off. And rather than dealing with IO that's really physically changing, I make it change in a simulation routine. So the idea is, if you had a fake actuator, you turn on the output for the fake actuator, a timer runs, it makes the fake input and responds to it, right? So if I have an auto sequence, for instance, I'll just pick one. Here's a simple one, a pick and place. Okay, and so when you get to a point here, right, the pick and place is Z lower, it goes to the next step. So this is not particularly complicated PLC programming. Probably some of the people on here have already seen auto sequences, so you kind of get the idea of how they operate. I will explain it real quick. The idea behind an auto sequence, after you've started your machine up and you go into auto cycle, or in this case, see, this one even runs in manual mode, it's a sequence of events. What you do is, for instance, I have a pick and place here, and I'll go ahead and bring up a picture of my pick and place so that you have a mental picture of it. There it is. So this is my pick and place. It's at home here, right? And then a part appears in a nest, and the pick and place reaches down, closes the grippers, raises the Z-axis, extends the X-axis, lowers down, opens the grippers, raises up, and returns to 0. So it's 8 steps. It's a pretty simple sequence, and this is a good one to introduce sequences to people. And it actually runs. I'll show you that in a minute here, but let's go through the sequence itself. Same sequence. I'm at 0. The part shows up. This is the auto sequence trigger, right? Right up here, you can see that the part shows up in the load location. You can also see here, for those of you who are familiar with Allen Bradley, there's something called aliasing. So if I go into my controller tags, I have connected all of my physical inputs in this routine to the simulated inputs right in here. So let's see, if I find edit tags, here we go, and I look at aliases, you can see here that the index alarm, which is an index mechanism, is alias to digital input 0.1.20. If that was alias to a real IO, it would say something like local slot 1 dot 20, right? Digital input. You can do the same for analog. So I've connected these to fake IO, and all you have to do if you had a real program here and you were simulating it is go back in after you tested everything and it works well and re-alias all of the fake IO back to the real IO. And then you've tested your program, it's run, you've actually seen it on the screen, operate mechanisms and things like that. You've watched part tracking and you know everything works. Then you finally get to power up your machine and you download the program and it's aliased to real IO and it just runs. You do the same for outputs. So any outputs I have in here, digital output 112. Okay, how does that operate? There is a simulation routine back here that detects that something's turned the output on. It turns on a moving part and responds when it hits the procs and cycles through the auto sequence. So this auto sequence, pretty straightforward. In step 10, tells the z-axis to lower. When the procs is made, it goes to step 20. You can kind of ignore some of this. I can explain this when we're done if you'd like. Single step mode is a method of indexing one step at a time through the sequence. And I just use this to show people how that works. I don't actually, wouldn't put this necessarily on a pick and place, but if I had a complex mechanism, I might put it on that. Okay, so let's go down here. Z raise, right? So Z lowers, then grip closes, then Z raises, then, and this one's a little more complex. There's something else going on in here. Then X extends, right? I'm in step 50, I'm in 50, and Z lowers, then I'm in step 60, I'm in 60, grip opens, I'm in step 70. I verify that the part made it, right, into the nest. And so I unlatch the part in gripper. This one, I need to memorize that I have a part in the gripper, because just because the gripper's closed doesn't necessarily mean that the part's there, right? Part still could have fallen out and maybe the procs is still made or something like that. So then when you get to the end, then it resets, right? Goes back to 0. So pretty straightforward step-by-step sequence. I'll go ahead and show this thing running. What you can do in the emulator, right? So this is the pick and place. You can see here I'm in auto cycle. So the only way I can make this run is to go back to my main screen and start cycling my parts through. This is actually in run mode, and you can see here there's some parts lined up on what's called an indexer. And I made this a long time ago. This was part of a previous class. I made the indexer, the pick and place, and this is kind of a master screen that looks at everything. And I animate things here. Let's see if we can turn the feeder on. There we go. So you see the feeders running here. You can kind of see the pick and place running in the back. I'll show you that in a minute. And my parts are indexing through here. And here is my pick and place. I've shown this before on here. That's my part tracking. Let me see. Pick and place. Once you get things out of whack here, there's the pick and place. It's hard to manage screens. So people sometimes ask, well, why don't you just run the application itself? The problem with running the application itself, it closes all of the screens and your navigation better work, right? But it does pop up alarms and things like that. So this is a pretty smooth moving, straightforward pick and place, right? The other thing I do in here is I do create a random number here. It weighs the part. This is meant to be a weigh scale, and you'll see this number change. There we go, 261 grams. If it's outside of its assigned range, then the part fails and I reject it at a later station. So that's the idea behind these simulations. This one's pretty straightforward. This is a good exercise for just a sequence, right? It just tells what happens in order. The part tracking, let's see, let's run that. I'm looking at part 16 here. So the part moves through location 16. You should see this change at some point. There we go. There's the part number, whether it passed and failed. It doesn't stay there very long. We'll try something like part, I don't know, 5. There we go. So it stays here longer, and you'll see the part make its way through here. And part of my serial number, this is something I teach in the class too, build your own fake serial number, and I put the date in it in this case. So since it's today, it's kind of just incrementing the counter and moving up. And so you can see the parts moving their way down here. It's kind of getting to be a complex mechanism. And of course, you can watch the program run. So the pick and place is running along here. There's step 50, step 60, step 70. You can watch it operate. Next step of the pick and place, you can see here that occasionally the Z-axis lower solenoid valve comes on. Then I go back to the simulation, and the simulation makes that sensor feedback. Now, to make things easier for the students, I actually created AOIs, right? AOIs, for those of you who don't know what they are, they're add-on instructions. You can build your own complex instruction. In Siemens, this would be called a function block, and it would be much easier to deal with because you could edit it in real time and download it. It wouldn't even stop your machine. With Allen Bradley, you can't edit it online at all. And really, even if you edit it offline and then import it, you better make sure that you're doing it correctly. Siemens is a little easier to deal with these function blocks, which function block is a pretty standard term in complicated programming for creating these objects, right? A function block type object. So this is the actuator simulator. There's a picture of it, and I'll show it to you here in the simulation routine. And we'll pick the pick and place simulation. So I go in here, and the idea behind these simulation routines here is to let them run in a completely independent program or independent routine. And you'll see this changing, right? Some of the values and things like that. You can't really monitor the values inside of it, but the general idea is if you're going to emulate a actuator, you need to have the time that it takes the actuator to move from end to end. And then you need to also dictate the times that the sensors are going to come on and go off. So I'm going to say it leaves the back sensor and it goes off at a certain time. It arrives at the front sensor and it turns on at a certain time. And then it sits there right on the front sensor. So that's the thing that's making these little fake sensors actually come on and go off. You see the sensors riding on here. So that simulation AOI is what makes the sensors change state. You can see here it's at the end, so the prox is on. And everybody has a different way of emulating these. One of my things is I do not like red objects on my main screen. In process control, sometimes people do that. They put red for something operating. But in machine control, usually red means something bad. It's an alarm or a fault or something like that. So I don't make my sensors, turn red when they get made. But some people will, right? Some industries, that's a common thing to do. Okay, so this application, I think I've shown on here before, but this week, one of the things I did is created a new station and created a new part tracking mechanism. And this one, for those of you, again, in machine control, is a dial table. And if I emulate it, right, it kind of operates independently of that other system. And the reason is I wanted to do a different kind of part tracking. I haven't kind of gotten to that point yet, but I'm going to concatenate all the numbers into a string and then display the string in my part tracking routine here. And that's going to be one of my future things. I'm also working on a process control application for people who do, right, process type things. So a bunch of tanks, batching. Let's see. I'm probably opening too many things at once here. Yeah, one of the things that happens is FactoryTalk View tends to freeze, especially the new FactoryTalk View. So you'll see here, I try to move it. It doesn't even move. There we go. Now let's bring up process batch. That's an example of animating a bunch of tanks. It kind of runs independently and it's in process, so I'm not going to go through it, but I am working on that, right? Working on some process control stuff so I can show people how all that operates. But this one is the one that while the students were creating their applications, I created this one, and it kind of runs independently. So if I place a part here, yep, this is frozen too. So you'll see me, hopefully the part will go up. Right, it's running all the other stuff, so it's busy ignoring me on this one. There we go. It's not a perfect animation, obviously, but the dial table turns. This one puts the part on the reject mechanism. I can put a new part in. Once it starts working pretty well, but put the part on the dial. Haven't made my drill run yet. I'm going to do a depth gauge, and the depth gauge is going to check whether it's a good part or not. And then if it fails, it's going to make its way off. And then I can put it in auto and make my parts appear automatically. So that's kind of what this class is all about. And I leave it up to the students. What do you want to simulate? People did all kinds of different things. One guy, it's kind of interesting. He was filling a bottle full of some kind of red liquid. And if it failed, he would actually make the bottle explode, and red ketchup or whatever it was would get all over the screen and ooze down the screen. Normally, I would not want to animate a screen like this. This is distracting to operators. They may think it's cool and fun watching the things move, but they actually recommend against that in most plants because the operator's busy just watching things move and not paying attention to the messages. You actually want your screens to be pretty bland, right? Not a lot going on, especially on the main screen. You want things like messages, if there's a problem, to pop up and be very obvious to the operator that there's a problem with the machine, and the rest of everything's supposed to be pretty bland. But this is somewhat common here where you'll see buttons actuate themselves. Right? If I go back to my pick and place screen, I think that's still running. You see as it goes down, right? These reflect the state of the sensors, or the picture reflects the state of the sensors. So what's the complicated part of this? Okay, the sequences, I've explained sequences, and they're not that complicated. As a matter of fact, here's a good opportunity to advertise my book. So I'm going to go ahead and put that on the screen. This book, which I wrote going on 4 years ago now, explains all of that. So auto sequences, input conditioning, output structures, all that stuff, which is, it's not basic, but it's also not particularly complicated. Once you get the hang of it, you could learn this in a week pretty well, right? How to manipulate auto sequences and make output structures come on and things like that. Once you've seen an output structure, so I'll show you one of those, you will remember it, right? Not this AOI, that's a whole different thing, but once you look at an output structure, you'll remember it pretty well forever, right? You have a coil with an output, you have some kind of a permissive saying this is allowed to do this. If the sensors aren't in the right condition, you don't want to break things. So if you're writing programs, one of the first things you do is make sure your permissives are correct so that things can't break other things. That's another proper use of simulation, because if you left out one of your permissives or something, you could actually run an actuator into another actuator. That would be bad. So that's one of the purposes of these simulations and things. So output structure is an output structure. Usually it's, you know, if I'm in auto mode, this happens. If I'm in manual mode, this happens. The book explains a lot of that, but this is very repetitive, right? X-axis control, they all kind of look the same. A simpler one, if I go to my dial, that's a really simple output routine, right? There's no running this in manual mode. This thing, if in manual mode, it's just a push button. You don't run in the auto trigger in manual mode. In the other sequence, I do. So this is a pretty standard output run. And this is where most people start their troubleshooting. They would go here and they would say, why won't this extend? And I'd go look at the permissive, and that might be the reason that it won't operate. Or it might be, well, it's in auto mode and I'm not in the proper step. And why am I not in the proper step? Because let's see, we'll go to rotate and say, why didn't my dial indexer index? Because some sensor wasn't made, or something wasn't detected to be in position, or this never got to the right physical position. I did have somebody ask me at the last minute to cover high-speed counters, and I didn't have anything prepared for it. So I don't have a way to go over how a high-speed counter works, but I can do that in the future. This is Samarjit, and I don't see him on this call, but he asked for a little bit of an explanation of high-speed counters. The problem with simulating high-speed counters is there's a lot of I/O. There is, positions of encoders that show up in the millions and things like that, and you would have to emulate all that to show it and make it operate. And I haven't written anything like that, but you can see here that I do have positions automatically showing up here, and that's all done through that simulation emulator, right? Generating all those things. Again, if I'm going to emulate something, I probably want to build a box that does a good job of acting like an actuator and then use it many, many, many times, right? That's what an add-on instruction would be for in Allen Bradley. For those of you who do Siemens, again, that's a function block. It's meant to be repetitive. You use it over and over again. Okay, let's go into a little more complex concept here. And this is why I called this a little bit of complex PLC programming. This is a little beyond the sequences. I want to track the parts, and I want to make sure that a bad part does not make it all the way through this line. So the way I do that is I track the parts through all these stations, and if they're bad, you'll see like this one here. Here's a historical record, and you'll see that changing. And you'll see if this fails this station, then I need to kick it off at a certain position. And in this case, let's see, I only have one reject station, and that's this one. If I look at it as a whole giant picture, peel it off, there we go, main. So my reject happens right here. That's my reject bin. So my parts make it their way through here, but the general idea is you do not want them going into the good parts if they fail. So I track them through this station, and if they get to, you'll see this one, yeah, it skipped all the way here to the end. That was a good part. If it gets rejected, it'll make its way here, and you'll see it push into the reject bin. And I animate that to, where's the conveyor? That's the dial, that's different. All this stuff's running at the same time. That's good. No major crashes today. Conveyor. Bring that up and watch it operate. The animation is not perfect. That one made its way through, didn't fail. A lot of these fail. I'd say 30 or 40% fail because there's 3 inspection stations and they're each about 10 to 15% random number generator to fail. I'm getting a lot of good parts. That's good. I got 184 good parts and 176 bad parts. So you can see here, probably 50% of them fail. That one passed too. I may have to look into that. But anyway, any questions about the simulation itself? And then I'm going to go into the part tracking a little bit more and some of the mechanisms that are, there we go, there's a rejected part. That was the camera failed, right? Random number generator ended up with a 2%. So that, like Cognex, that's the way they do that. They assign a percentage to Pat Max. There's another failed part, 12%. Right, the camera failed it. Okay, so now let's get into part tracking and look at how that is done. So the way part tracking is done, I'm going to pick, I'm going to use this dial as an example. I take the first station, and when I place the part in the first location, I put some data in there, and I'm dealing with records here. The record is a UDT that describes the part. So I'll go to my UDTs here, which is in assets, I believe. Now they have it, assets, UDTs. So user defined, that's what UDT stands for. I've got a bunch of them in here. And I'm going to pick my dial part right here. So this is a fairly simple one. This describes the part that is on the dial, right? And there's only 6 locations on the dial part tracking. There's a bunch more on the other one, but a couple things I want here. I want, when did I start this part? It's got year, month, day, hour, minute, second, microsecond. This is standard from the GSV command, which is get system value for wall clock time, local date and time. So that's how I did that. You move it into an array. Generally, you create your own array with all these things in it: year, month, day, hour, minute, second, and microsecond. And the date and time shows up as a whole bunch of double integers. And then you put them into the proper location, and then you make a tag for it. So a typical tag for part tracking would look like, go back down here to dial. You know, naming things is important too, right? So I've got dial records, and I take dial record 1, monitor the tags. There's my time start. That UDT had hour, minute, second, etc. And there is my start time. After I move the part in and the part leaves, of course, I need to clear this. An easy way to clear this is to leave dial record 0 empty. Put nothing in the contents and simply move 0 into location 1. If the this little, I kind of made funny names for this, but the getter, right? I was in a humorous mood here. This is the getter and this is the putter, right? So this gets the part from here. Then after it's done being processed, it puts it over here. So when this sweeps this away, I need to move a 0 into location 1. This is location 1, 2, 3, 4, 5, and 6. So you'll see the parts making their way through here, and that's why you see this. I log the time of start right when the part gets there, and I also assign it a serial number. Serial numbers in the real world can come from various places. Maybe they are a barcode that you read, right, off of the part, or maybe you assign the serial number at the position where it gets placed, and then maybe you print a label and you put the serial number on it. In that case, it involves like querying a database, or the database assigns the serial number, and that gets outside of the PLC, right? That's a magically appearing number that is handshaken across to a something like, I don't know, Ignition. Maybe Ignition has a SQL database, and somebody in the company has said, I'm going to make this serial number out of, I don't know what you're going to have in there. Maybe the part number is going to be in there, the part type, like our data recipe, right? This is the chassis of it. Maybe you're going to build the date into it or something. So my serial number here, I've got a kind of a funny serial number. We'll see it show up again here, 11194 something, and then the date was on it. And so I kind of 11195, you can see that part's incrementing. That is simply a counter. And so I increment the counter, and then this number at the end of it, right? There's a 27. The next number will be random, 11197. Then it's 1194, and the 1194 is totally random. I've explained how to do a random number generator before, and I may do that again, especially if somebody asks about it. But a random number generator in a real PLC program is not useful, right? I don't generate random numbers unless I'm simulating something or faking the machine, but that's part of this serial number. So I assign the serial number based on a variety of things. And part of the reason I do that is because I want to teach these students how to, let's see if we can find it, how to deal with text, right? So this is how I make the serial number, right? So I have a counter in here. You can see it's 11 to, every time I make the serial number, it counts up 1, 11205. I started it at like 11,000 yesterday when I was teaching the class. You can see here 206. So this counts up. This generates a random number, again, an AOI, an instruction that does that. I built this a long time ago, and the idea behind making a random number is there is nothing random about timers or PLCs or anything else. But what there is that's random is when a part arrives in a location. So if I have a timer in here, for instance, that is only 100 milliseconds, and the part arrives at some point in that 100 milliseconds, and the 100 milliseconds is repeating itself, then I'm going to get a totally random time, right? Just based on when the part arrives from 0 to 99. And then I turn that into a percentage. And then I can apply the percentage to something else. So I've got a counter, I've got a random number generator, and then I make the serial number by turning the number into a string, right? Which is text. Most of your barcodes and your RFID systems and your database information, most of that will be text, human readable text, not dents and numbers and things like that. So you need to turn this into text to build a serial number. There's the serial base random number, right? This is the thing that spits out of the random number generator. Right. And then what I do to further kind of generate a random number is I take the raw value out of the base and I multiply it by 13.27. I just made that up, right? To give me a really strange number that's part of my serial number. So you can see my random number part of the string is 969. The next one is 809. Sometimes it's 4 digits. Sometimes it's 2. One of the reasons I did that and made it a varying length is because I also want to teach people how to go in and take that string back apart and determine where is the date, where is the random number, where is the serialized. Well, the serialized is easy. It's the first 5 characters, right? It's always the first 5 here. But then you concatenate all this, which means jam all the values together end to end in text, using text tools, right? Concatenate. And this rung builds that entire serial number. It just concatenates a bunch of things, right? So I turn everything into text and then I jam all the numbers together end to end. You have to convert the decimal number into a string and then jam them all together, right? So I jam 3 and then some tricky things in here, like for instance, going and getting the month. I actually use the month as text, and somebody asked me how to do that before. And the way I do that is create an array of months. And so if it's a 3, it's March right now. And if it's a 3, it goes to that position of the array and indirectly moves MAR, the letters MAR, into the string. So that's a general concept about it. And if somebody wants to see how that works, I can show them, because my other serial number actually has that in it. It has the actual date using the letters of the month. So this is a little bit about generating the string. Reading the string and taking it apart is done in a similar way, right? I have to deal with text. And then when I go to my part tracking, I can see, right, text in here. This one's the one I was telling you about, that the date is built into, and the product number, product name is built into the serial number. On this one, which is the dial parts, it is not. So we'll watch the dial parts run. Right, the dial parts number, I put a slash in there and stuff like that. You can see the parts moving through here. When they get here, they have a time complete. And then I actually jam it onto a FIFO for the historical records. So I'll show you a little bit of that too. And I'll take questions after we're done with this on especially the part tracking. That was the main purpose of this class, is for people to be able to grab the information about a part, create it, and then use that information when it gets to a certain station to say, am I gonna, what am I gonna do with this part? If it failed something, then I wanna do, right, I wanna reject it. So reject it, right? We'll see if this one fails. It failed, right? So kick it off if something's wrong with that string. And then this explains what's wrong with that text. So that's the idea of part tracking. So a little bit about the historical record. How did I do that? This uses something else that I really wanted to make sure that the students in that class understood, which is when you deal with arrays. Arrays are a group of similar things, right? So a part record is similar. If I make an array of part records, and we'll go to controller tags, this is an array of part records, dial records, right? Every one of these is the same part. I've got dial records. I think it goes up to, I may have even done 100, even though I don't use all 100 of them. I only have 6 stations in the dial, but I went ahead and created a really big dial record. Let's see, dial records, yeah, 99. And then I have a historical dial record. The historical dial record is not parts in process on the dial. It is records that are archived for future retrieval. And it's the same record, right? It's the same UDT, time start, time complete, serial number, etc. One difference is, of course, if I go into time complete, for every record, I better have a time complete. Right, here's time complete, right? 2023 311. This was created at, you got to expand it out to read it a little bit. 311, which is today. I've been auto running this at 9:36, right, in 18 seconds. And so I'm building a stack of records here, and I do not do it the same way that I did my other part records. My other part records, if I do part tracking, I do individual record moves, right? I move here. If 1 is present, I copy 1 to 2 when the getter goes to station 2, right, which is that sweeping arm. When that goes to station 2, I latch station complete for 2. I move 1 into 2, and then I erase 1. So I clear it with record 0. Here, I do a part shift, and I do this the old school way. And what I mean by that is I move 4 to 5, I move 3 to 4, I move 2 to 3, and I move 0 to 2. So that's the old school way to do it. But if I wanted to move 100 part records, I would not want to build something 100 instructions long. So there's another trick that I explain, and I don't really have time to go through it here, but it's in that book, right? I explain how do I transfer 99 part records, all at once. I'll just verbally describe what you do, but you basically take a stack of information and you need to create a dummy stack. You cannot overwrite yourself. So I can't take record 1 through 50 and copy it into 2 through 51. Not allowed to do that. Can't overwrite yourself. But you are allowed to copy 1 through 50 to a dummy array of 2 through 51, and then copy it 2 through 51 back to the original array. I'm allowed to do that. And I explain that in that book. That's just there's a little diagram that explains all that. So that would save me a lot of this coding, right? I don't have to move individual records. Okay. The reason I do this and don't use the more complex thing that I'm about to show you, which is a FIFO, is because a FIFO does not put things in the correct station number. A FIFO is going to operate on the entire array. Say I set up an array of 100 items, it's going to operate on all 0 through 100 items, and they're not going to end up in the station number, so I don't have an easy way to look them up by station number later, which is why I do things this way. So now let's take a quick look at the FIFO. And this is a somewhat more complex instruction because it uses a control tag. Don't know if anyone here has ever had to use control tags, but control tags in general apply to all of the more complex array-based instructions here. So that's where I was talking about a little bit of advanced PLC programming here. File miscellaneous, for instance, has a file search and compare. And you see right up at the top of it, there's a control tag. Here's a file arithmetic and logic. That's a control tag. Here's a FIFO load. That uses a control tag. A control tag consists of a bunch of different things. It consists of a position, right? The current position. It consists of a length. It consists of a bunch of bits. Here is one of the bits, the done bit, right? When it is done, if this ever gets done, I clear the last record and I move it into a dummy location for future retrieval. You have to empty out, you have to unload the last part in there. So that's what this is doing, and it's dealing with 100 records at once. I'll show you the control tag here real quick so you know what those are. And I think it's called dial control, hopefully. It's in the local tags. So that's another question sometimes people have for me is, why do I put some tags in the controller tags and others in the local tags? In general, if it applies to the entire machine, which dial historical records, in general, I put all my records of things in the main routine because some SCADA programs have a harder time drilling down into these program tags, right? So the program tags are for things so you don't clutter up the controller tags. You could see in that big program I showed you before that had 70 different programs in it and 70 sets of local tags. I would not want to put all those tags in the controller tags. It would make it a nightmare to find anything. So in the local tags, here's dial, and there should be a control tag in here. So if I look at my data types and I just browse down, I can probably run into the control tag pretty quick. There's a special tag, the simulated actuator control tag right here. So that's what it looks like. So a control tag has the length of the array. That's what that's applying to. It has the current position of the array. So you see this one here got up to 99, which means the next record will go into 99. That's basically the way the FIFO load goes. If the done bit comes on, which you would see it come on, but it would only go on for one scan. If the done bit goes on, that's the trigger to unload the FIFO because it's full. I've got 100 records in it. I need to unload the last one. Things like EM. EM is the empty bit. It says that this array is completely empty. I've completely emptied it out of all records, or I'm at zero, at position 0. The done bit means it's full. It's the opposite of empty. So FD bit is the found bit. If I did a file search and compare, that bit will come on to say whatever you were searching for, it found, right? So pretty obvious abbreviation, FD for found. ER is error. If I make a mistake in my programming, then the ER bit will come on. It'll say, hey, you're looking at a position here. Maybe you moved position 102 into a 100 element array. You can't do that, right? That's an error. The enable bit, pretty straightforward. Is this instruction active? Is it running? The EU is the empty unload bit. And then there is a inhibit bit. Inhibit is this one. right down here. So the way the inhibit bit works, it generally works with the found bit. If I find something, the search stops in that location. I say, okay, the position is 15. I found it in location 15. I then reset the inhibit bit and it goes and finds the next thing. You can find all this, right? If you go up here into the help files for, right, instruction help, for Allen Bradley here, instruction help right there. If you look up FIFO load, FIFO unload, you will see everything you wanted to know about that. And it's pretty good. Sometimes they give examples. You may find some stuff online about it. Lots of different ways to find more information about control tags and things like that. But that's a quick look at the control tags. And of course, I used it for the part tracking, for the dial. That was the general idea. And these three rungs, right? This is clearing location 6. Why do I do that? Because my dial location 6 automatically disappears here. It kind of pretends it moves down the conveyor. So I clear 6 and I move it into the historical record. That's the idea behind that. At this point, it is about 5 minutes left to go, 5-10 minutes. We can certainly go a little long if we need to. Are there any questions about any of the programming concepts that I went through here? Okay, no questions. It was, there's obviously not enough time to go over every single detail of a program like this. This is a pretty complicated program. It's fun to watch. It's fun for these students to take this class because they get to create their own application. You can see here, everybody's smiling faces in the class after they got their certificate. I will say one of the people in the class got kind of overwhelmed. When we started, he thought, oh my gosh, this seems to be a ton of work. Can you share your random number generator? Yes, I can do that. Let me show it anyway here real quick. I explain it somewhere else too, but there's not really a lot to it. Let me bring up the random number generator AOI. You can't watch it run because it's an AOI and it's been used in multiple places, but I can bring up the logic for it. Yes, not particularly difficult. Sounds difficult, but let's see. Assets, a random number. There we go. So for those who haven't seen an AOI, this is grayed out. And what that means is it can't be edited, right? You can't edit Allen Bradley AOIs online like you can Siemens. The general idea, I have what's called a free running timer here. It is running a 500 millisecond time. So with a done bit in it, it resets itself. It just constantly runs, right? And if you actually look at these numbers, these look pretty random, but that has to do with the screen update time, right? That doesn't have anything to do with the randomness of it, but this is running continuously 0 to 500 and then resets itself. I then, at a given time, whenever I actuate, right, whenever I hit this trigger, I move the value into the number generated. So say I hit here randomly and I move 156 into this location. All right, so now I've got 156 in there. I divide it by 5. Why? Because I want to generate a random percentage. So I divide it by 5 to get 100. I then take that and I say, you moved a threshold into this random number generator. Is it over or lower than the threshold? So that way you get a result. Is it above the threshold? In which case it's good. And if it's below the threshold, then it's bad. So you could do that math yourself if you wanted to, right? As far as the threshold. Now let's apply it to something like this, right? How did I get 67? 67 is pretty easy. I actually generate this randomly 0 to 100%. This is meant to be like a Cognex camera. That's a 67% match. That's good. If I go to something like the indexer, I think it's got a weight on it, and it is a little more complex. And we can actually watch it run too. I've got a measurement here, and this is 70 point something. There we go, 71.168. So if you do that, math's just math, but basically I say if it's between, I think it's 69 and 71 maybe, then it passes or fails, right, based on that. So I just apply the percentage to a little range. And I say I want it to every once in a while fail a little outside of the range. So maybe I make my range from 68.8 to 71.2. And if it's outside of the range, then it fails, right? Outside of 69 to 71. So that's the general idea for this. So the only thing I'll say about these simulations, this is not meant to be something, right, that I would necessarily run on a real screen. But it is great for this kind of thing, right? If I'm doing part tracking, I really do want to make sure my part tracking works before I ever apply it to a real machine. Because what's going to happen is I'm going to have a lot of bad data as I'm starting up. So I'd rather make sure this works ahead of time before I can even power up the machine. That's the concept behind doing the simulation. Make sure everything works. Make sure your auto sequence puts things in the right place, that you generate your parts in the right place. Make sure that the bad parts get kicked off, right? Kicked off the thing. This doesn't have a reject mechanism. I'm just using this for kind of a display here. I'm going to drill it. I'm going to do a depth gauge, and the depth gauge is going to pass or fail. And I'm just going to use it in the part records. I'm not going to reject it or anything like that. Kind of have already done that before. The animation itself, you know, that's a kind of a different lesson. I did a webinar before on FactoryTalk View ME, and I showed a little bit of how some of these animations work, right? Vertical position, horizontal position, changing color, things like that. You can see here the position of the dial. This is a leftover from before, but as I rotate, right, that is just a positional update. You notice here on this simulation, the thing I'll say about simulation, almost everything here is timers. It's just free running timers. And then you manipulate the free running timer, even for the random number, right? Everything is based on free running timers or fixed timers. The AOI that I had for the simulating the actuator, that's just a timer running from beginning to end and changing the sensor status and all that kind of stuff. So that's pretty much it for this webinar. We did a full hour. We did a little more than an hour. So obviously we could have gone on for probably days, and the class did go out on for days, right? So we spent 5 days, March 6th through the 10th, this last week. I do this class for Automation NTH 2 to 3 times a year for whatever interns they have in there at the time. Some of you know I do own my own company called Automation Consulting, and I publish books and teach classes, but I do 10 days a month for this company, Automation NTH. They're close to me. They're about 25 miles away. Lots of good engineers there. They do very high-tech programming, very big programs. I showed a little bit of that before. Massive program, right? Lots of routines, 70 routines, 70 programs, several, maybe 1,000 routines, and probably 200 and some odd individual Ethernet-based addresses. Big machine running an L84 processor for Allen Bradley. So the next webinar is going to be April Fool's, right? Because it's on April 1st. In other words, I don't know what the topic's going to be. It may be something kind of you know, funny or whatever. It might be just be open questions if anybody has any questions about anything. I leave the next day to teach a Siemens class in Chicago, I believe. on Sunday. So this is on Saturday, and then I go to Chicago and teach a Siemens class. So who knows? Maybe I'll cover Siemens. I don't know. But in any case, that is the end of this webinar. Feel free to visit these sites. There is some stuff you can download there if you want to get on my mailing list, etc. Join IO Central. You can find these places at these addresses, and check out my YouTube channel. And thanks a lot.